Okay, let's go ahead and discuss some background information for the mission. So, previous Mars missions have tested ice and rock samples in situ. Most of that has been testing of rock samples, but to date, no samples have ever been returned from Mars, and there has never been any ex situ testing of samples from Mars. So, if we're going to send a mission to Mars to bring back ice samples, that's going to cost a lot of money. The question is, what's the motivation? Why is it worth it? The answer is that two main reasons. One, having ice samples will benefit our study of past life and present life on Mars. Two, it'll make future human missions a lot easier.
Okay, so with all this information, here's what we want our mission to be. We want to design a reliable and cost-effective vehicle to extract and return ice samples from Mars to Earth for scientific analysis. And now, here's the concept of operations to achieve this mission. Here's the diagram that visually represents the various phases of the concept of operations that the mission is going to go through. The first phase of our mission is getting to Mars. We will do this by launching our vehicle with the payload and entering low Earth orbit. From there, we will transit to Mars and enter Mars orbit. The second phase of our mission is performing operations on Mars. We're going to land the payload on Mars, collect and store the ice samples, perform any secondary mission activities, and prepare for the return phase of the mission. The third phase of our mission is getting the samples back to Earth. We're going to do this by launching the ice cores into orbit, initiating systems to maintain sample integrity, transiting to Earth orbit, re-entering the atmosphere, and finally landing the payload. The final phase of the mission is activities on Earth, where we retrieve the samples and distribute them to sample processing labs here on Earth.
In order to adequately model the complexity and cost of this project, we needed to make some simplifying assumptions. We presumed that a launch vehicle would be available at the time of the mission launch and that current costs would still hold. We assumed that in creating a Mars sample handling facility, the design of the existing lunar sample handling facility would be copied insofar as that is possible. We assumed that we would use existing space communications networks like the Deep Space Network rather than creating any sort of new infrastructure for that. And we assumed that this design would not include any sort of in situ testing and would focus solely on ex situ testing of samples.
Our needs represent what the mission must accomplish to satisfy the stakeholders. There are 4 major stakeholders for this mission, and we divided up our needs between them based on what each stakeholder wants from this mission. First, the scientists who are going to analyze the ice sample will want the ice to be returned intact so that evidence of life will be preserved if such evidence exists. They will also want a large enough quantity of ice to study, and the ice to not be contaminated by foreign materials. It's also important that the structure of ice is preserved, as this will be important to the scientists studying it. The next stakeholders are the engineers and astronauts who are interested in future Mars missions and potentially even colonization of Mars. Their interests are in many ways aligned with the interest of the scientists because the data gathered from the ice samples will be useful for them as well, especially regarding whether or not there is life on Mars and what the exact chemical composition of the ice cores is. Another stakeholder is the organization that will operate and launch the mission. Their interests are mostly related to the technical aspects of the mission, such as the size of the rocket and whether or not the rocket is acceptable from an environmental and safety standpoint. Finally, our last stakeholders are the politicians and government officials. Their main needs are to minimize the cost of the mission, minimize the time that the mission will take to develop and be completed, and to minimize the chance of failure. Based on these needs, we decided on a set of system requirements. We decided that the system shall be required to mine at least 2.5 kilograms of ice, as that is a reasonable amount of mass to transport, but will also give the scientists a significant amount of ice to study. The ice cores will also be at least 100 millimeters in length and 25 millimeters in diameter. Longer ice cores will provide more useful data, and this length will be long enough to give good data without being too difficult to transport. The ice cores must also be isolated from potential contaminants at all times. This is an important requirement for meeting the needs of the scientists and the engineers. Finally, the total cost of the system shall not exceed 3 billion USD. This is an important requirement for the organization that we will receive funding from. This figure shows our functional analysis for the overall system. Our overall function is to collect a sample of ice from Mars and return it to Earth. We defined electrical power, Martian ice, the spacecraft, and delta V as our supporting subfunctions, and the funding as an auxiliary function. The system uses these to provide ice samples on Earth as an output. Along with the overall functional analysis, we also did functional analysis for all of our system's subfunctions. These subfunctions were to launch from Earth, land on Mars, collect ice, store and preserve ice, launch from Mars, and land on Earth. In order to relate our engineering specifications to the customer's needs, we used a house of quality. On the left, you can see our customer requirements divided up by stakeholder. On the top, you can see our engineering specifications divided into the categories of launch requirements, data collection, and production. In the middle, we mark which customer requirements are related to which engineering specifications, and whether there is a strong or weak and positive or negative correlation. On the right, we compare our system to how well other systems of a similar type meet the customer requirements that we defined. And at the bottom, we perform a similar analysis to see how well these competitors meet our engineering specifications. Overall, the house of quality is used to determine the importance of each of our engineering specifications, determine what engineering specifications correlate to meeting which customer requirements, and determine how effectively competitors are able to meet both sets of requirements.
Okay, now it's time for concept generation.
Now, to understand how concept generation will be used by the team, we need to take a step back and see how it integrates into the other parts of creating our design.
The first step in concept generation is to clarify the problem. This is already done in the introduction when we came up with our needs, requirements, our stakeholders, and our mission statement. Now that we've defined our problem and broken it into subproblems, we can begin to do an external search for concepts. This can be done through talking to researchers, reviewing literature, or even looking at historical data. We can come up with extra concepts through internal search, where we use our own knowledge and information to come up with some novel ideas.
Okay, so like what if we had these astronauts and we put them on a hot air balloon, right? And the astronauts jumped out of the hot air balloon and they were wearing wingsuits with a jetpack on them. And then they rode those jetpacks to the International Space Station where they were loaded into a catapult. And the catapult launched them straight to Mars. And then when they got to Mars, they pulled out the shield from their backpack and they used it to aerobrake. Then they pulled their parachute and made a perfect landing.
Okay, we'll write that one down.
But how are we going to create designs in a more systematic way? This is where the concept combination table comes in. Using the subfunctions the team created during the concept of operations, a table can be made which lays out the subfunctions and their potential solutions. By connecting these solutions together, the team can create a final design. Here are the ones that we used. Launching from Earth, transferring to Mars, the preparation to land on Mars, the actual landing on Mars, collecting the ice core from under the surface of Mars, storing that ice and keeping it preserved for the trip back to Earth, launching our ice cores back off of the surface of Mars, transfer the ice cores back to Earth, prepare to land the ice cores back on Earth, and finally, landing them on Earth. Now, all the team has to do is connect these various design elements together in order to create a preliminary design. Starting with something that NASA would do as a datum point, we could say that for launching from Earth, they would use cryogenic fuels. Transferring to Mars would utilize chemical propulsion. Link those two together. Now preparing to land on Mars, that would use aerobraking. Link. To land on Mars, NASA seems very fond of the sky crane. Link it. Now, when it comes to collecting ice, the preferred method for NASA so far has been a rover. So we connect it. And then we start to preserve this ice. So far, NASA has only used passive cooling systems. So we'll use that as our design element. So and then we got to return it from Mars. And right now, the best solution seems to be to use a rocket. So we'll go with that. Connect it. And now we got to transfer back to Earth. The best thing would be to reuse the original vehicle that had already got in orbit. So we connect it. Then we got to prepare to land on Earth. And then we'll probably use aerobraking again. That seems a very NASA thing to do, you know. Connect it. And then once we finally get to Earth, we're just going to use the parachutes with an aerial retrieval system. And there we go. Simple as that. We have a design. In addition to the emulating NASA design that was shown on the board, 9 additional concepts were generated by the team. This includes colony foundations, rocket disposal, the Wild West, roll the dice, gambler's fallacy, direct descent, procrastination, we'll get there eventually, and low tech. Now, with all of these concepts generated, we go on to concept selection.
After the concepts were generated, they were all put through the process of concept selection. During concept selection, 9 criteria were used in a Pew matrix in the first and second rounds of selection, followed by a selection matrix for the third and final round. The criteria used in the Pew matrices were as follows: returning the ice in a state such that evidence's life is preserved, returning ice preserving internal structure of the sample, returning a quantity of ice sufficient for research, providing information on the composition of the Martian poles, making sure the system is of an acceptable size, ensuring the system is not harmful to the environment, reducing the time to launch, reducing mission costs, and lowering the probability of failure. The third and final round of concept selection involved the use of a selection matrix. In this matrix, we compared the 5 finalist concepts, including the datum, using the same 9 criteria used in the 2 previous rounds. However, in the selection matrix, the criteria are weighed according to their importance. For us, the most important criteria were the ones that involved making sure we had a good, reasonable sample to achieve the mission's scientific objectives. The final selected concept is a multiple launch concept where the lander to collect the samples and the spacecraft to retrieve them and take them back to Earth are launched separately. During the mission, electric propulsion is utilized for its high efficiency, and aerobraking is used to slow down at Mars. Landing is accomplished via the airbag landing system similar to that used on the Spirit and Opportunity rovers. To collect the samples, a stationary lander with a drill is used, and where possible, passive cooling and insulation is used to keep the samples frozen. The second spacecraft will retrieve the samples and take them back to Earth, where it will rendezvous and dock with the ISS, where the samples can be returned as needed.
And now we're going to talk about the risk assessment and mitigation strategies. So for our risk methodology, we used the NASA risk assessment matrix to identify risks and come up with mitigation strategies. We assigned these risks a consequence number from 1 through 5, where 1 indicates a mild consequence, while a 5 indicates a catastrophic consequence, which could lead to none of the mission success criteria being achieved. We did the same for the likelihood of the risk occurring, where a likelihood of 1 means that the risk of occurring is highly unlikely, but a 5 means that the risk is very likely to occur. Depending on where the product of those 2 numbers falls on this risk matrix, the risk is either acceptable or unacceptable. So here are some of the major risks we identified. The ones to focus on are the ones in red, such as the return launch failure risk and the damage during Mars entry risk. The way we plan to mitigate the return launch failure risk is to include a system that would eject the sample and keep it safe for when a later sample retrieval mission would be sent out. And for the damage during Mars entry risk, we would plan to mitigate this risk by using a landing system that had extensive flight heritage.
The technical soundness of this mission architecture is due to the fact that it uses existing and proven technologies, such as the landing system from the Spirit and Opportunity rovers, and electric propulsion similar to that used on NASA spacecraft such as Dawn. Development costs for the mission are reduced, as it uses existing landing technology and does not carry very many expensive instruments for exploration and data collecting in situ. So I would estimate the development costs somewhere around $1 billion. Launch costs involve 2 heavy class vehicles such as a Delta IV or Falcon Heavy. Averaging the cost of these vehicles, you get about $220 million per launch. The sample handling facility is said to be about $140 million over its development. This is required for any Mars sample return in order to process the samples. Finally, operations cost, ground crew, communications, etc., would likely be comparable to the present-day Curiosity rover, which runs about $70 million per year. Therefore, the cost of this mission is somewhere in the neighborhood of $1.6 billion in initial costs, plus $70 million per year in operating costs.